Okay, hi there. Dr. Matthew J. Traum here. This is EML4140 heat transfer. We're in module 3, which is heat exchangers, and this is lecture 8, the Effectiveness-NTU method. There's corresponding reading in the textbook. So please read 11.4, which is Effectiveness-NTU method, 11.5, heat exchanger design performance calculations, 11.6, which is additional considerations, and then there's a special section 11S.2, which is compact heat exchangers. So we'll talk about all that in today's lecture. And for those of you looking for the ADA compliant transcription, this is the recording that will generate that transcription. So when you look at the slides, there will be a link here to a permanent Zoom site that will have a transcription written out for those who are looking for it. Okay, let's get into it. So as you guys know, I always like to start my lectures with a cartoon or a meme. And this one is particularly relevant to what we're talking about. I think this is just a South Park character. But the caption here is, I did 13 hours of work to design a heat exchanger, and it's wrong. And this is kind of how I feel about this lecture because you'll see there's two example problems at the end, and I spent hours trying to get it all worked out. And the underlying problem is not that this stuff is particularly hard, but there are a lot of variables that look very similar: temperature in, temperature out, temperature hot, temperature cold, and it's really easy to get those temperatures mixed up. And once you get them mixed up, it's over. So, anyway, that's I saw this meme and I'm like, yes, that's how I feel right now after I'm solving all these example problems. Okay, so this is actually a follow-on. So the second part of a two-part series for this chapter in the book, chapter 11. And so we've already talked about, and you've already seen this slide, by the way, log mean temperature difference, LMTD, which is the first technique in the chapter. And then this is the follow-on technique for heat exchanger solutions, which is called the effectiveness NTU, or number of transfer units method. And we use LMTD, basically when we know all of the inlet and outlet conditions. So, the inlet temperatures, outlet temperatures for both the hot stream and the cold stream, the mass flow rates. And your goal is to determine the UA, right? So the heat transfer coefficient and the area inside the heat exchanger required to achieve what you're actually observing outwardly, right? Mass flow rates and temperature changes. So a lot of times that's as an engineer trying to design something, that's not actually the information that you have available. And so there's an alternative technique, which is kind of the reverse in a way of the LMTD method, which is if you already know the UA of your heat exchanger, and you know the mass flow rates that you're intending to put through it, and you know the inlet conditions. Effectiveness-NTU gives you the outlet conditions of the heat exchanger. And the thing that's kind of interesting about this is LMTD is predicated on the idea that you can apply the first law of thermodynamics, right? You basically know all of these things with the exception of one, and you apply the first law of thermodynamics, and out pops the one thing you don't know. With the Effectiveness-NTU method, enough information is withheld that if you just sort of blindly apply the first law of thermodynamics, you would not actually be able to get the output conditions. So as you guys will see, there's some very clever kind of thinking that goes through, which stream is which and how to put things in order in a particular way that will actually reveal information about the heat exchanger that you can't actually get straight from the first law, at least not without some additional creative thinking. And AI generated this for me, but it essentially just differentiates the two techniques from each other. So LMTD is good if you know the inlet and outlet conditions, and you're trying to figure out the UA. So you're interested in things like the design of the heat exchanger, like what its internal configuration is, like how big it is, right? So all that stuff. And then Effectiveness-NTU is if you know just one set of conditions, either the inlet conditions or the outlet conditions. And this is good when you're trying to fit, right? You go to a catalog, right? And heat transfer manufacturer, heat exchanger manufacturer has all kinds of different possible heat exchangers that you could buy to achieve a particular goal. This is the technique that you use for that, right? So performance prediction, system analysis, and so forth. Okay, so that's the one that we're going to do now, Effectiveness-NTU, because you've already seen LMTD. So here we go. Okay, so um, I've got this little cartoon up at the top, which probably doesn't make a lot of sense in this context, but there's, as you guys know, I'm sure, because we're at UF and UF has a particular brand of soda that it likes. Um, you basically have two choices, right? LMTD or Effectiveness-NTU. And so the reason that I thought this was funny and I liked it is, Coke, please. Is Pepsi okay? Says the waiter, and then there's Pepsi sitting right there at the table, looking despondent, and then the guy says Pepsi is fine. So Effectiveness-NTU is often like sort of thought of as like the second choice, but interestingly, it's quite a bit more powerful technique, right? So like the Coke Pepsi dichotomy. Um, Effectiveness-NTU is actually sometimes a lot more powerful than LMTD is. So, good to keep it in mind, not as kind of a second best, but as a reasonable and viable alternative to LMTD. Oftentimes, it's the only way to solve these kinds of problems. So let's run through it. And my normal philosophy, if you've had me in fluids, is to like not get into the nuance of the equations and how they're derived. And I went through and kind of broke my own rule and did it for LMTD. And so I'm going to break my own rule again and walk through it for Effectiveness-NTU. That leads to a much longer lecture, unfortunately, and hopefully you guys are watching me on 2 or 3x speed here, to get through this, because I know these are sometimes long and painful. But specifically for Effectiveness-NTU, I think it's important at least once to think through how it actually works rather than just sort of blindly jumping in and using the technique. Because as you guys will see, there's some like clever thinking that's kind of built in here to extract information from the heat exchanger that you would not be able to get just by applying the first law of thermodynamics. But if you kind of think about, which stream is doing what and which one has higher temperature and which one has more thermal capacity, you could actually extract additional information, which makes this technique viable. Okay, so if the heat exchanger outlet conditions are unknown, right, that's the classic Effectiveness-NTU situation. We're going to use this technique to calculate the heat transfer Q dot, right? That's usually what we're going for. So that's the amount of thermal energy traded between a hot stream and a cold stream inside the heat exchanger. So Q dot between two streams, characterized by this property called effectiveness, which is epsilon. So the Greek letter E. So kind of the cool thought process here is that we set this thing called Q dot max, and Q dot max is it doesn't actually happen, right? It's an idealization. So it's the maximum possible heat transfer that can be achieved in a counterflow heat exchanger where one fluid experiences the maximum possible temperature difference. TH I is for inlet minus TC I, right? So H is hot, C is cold. So the high temperature inlet minus the low temperature inlet fluids. So again, this is theoretical. This doesn't actually happen, right? But imagine, if you will, that a fluid basically experiences this temperature change. Okay, so there's two possibilities then, right? So one possibility is the thermal capacity of the hot stream is bigger than the cold stream. So that's the one that we'll talk about. But then this also works if this flips around and the thermal capacity of the cold stream is greater than the hot stream, right? So it works either way. But we're going to walk through just this example where CH is bigger than CC, just so that you can like see an example of it being done, at least in variables. Okay, so we're going to consider the thermal capacity of the hot stream to be greater than the cold stream. And so what this means is that the cold fluid experiences a larger temperature change, right? Because it has lower thermal capacity. So if it's absorbing heat, thermal energy, it's going to heat up more than the hot stream would cool down because of its lower thermal capacity. So accordingly, we're going to establish a thermal capacity called Cmin. This is the lower of the two. And this is where, right, this can go either way, right? So Cmin is CH if CH is less than CC, high temperature thermal capacity is less than lower temperature, cold temperature thermal capacity. And that leads us to the expression for Qmax of the cold temperature thermal capacity times this maximum possible temperature difference, right? So this is the maximum heat that could be exchanged in a system where the cold stream is the one with the lower thermal capacity. The other possibility is if, which is the one that we're actually doing, is if the hot stream, the thermal capacity of the hot stream is greater than the thermal capacity of the cold stream. Everything else is the same. The only thing here that changes is that Qmax is now the thermal capacity of the hot stream times this maximum temperature difference, right? So by setting setting Cmin, we get these two different Qmaxes, and they really just depend on whether CC or CH is in there, right? So you have to identify which stream is the hot stream, which stream is the cold stream, and which one has the lower thermal capacity, and that's what ends up going into this equation for Qmax. So out of this function pops Qmax, which is equal to Cmin multiplied by this temperature difference, right? So this is the maximum possible heat exchange that could happen theoretically in your heat exchanger. And this construction often causes a lot of confusion, right? Because why in the heck is Q max associated with C min, right? Shouldn't it be the other way around? Shouldn't Q max be associated with C max? Well, if you think it through, if you have a fluid with a larger C that experiences a maximum pop, let me try again. If the fluid having the larger C, there we go, experience the maximum possible temperature change, then the first law would require the fluid with the smaller C to experience an even bigger temperature change, right? Because if C is big for the fluid that we're talking about in the first part of the sentence, and C is small for the fluid in the second part of the sentence, they're trading the same amount of heat, right? And so this smaller C fluid actually has to get hotter, right? It has to experience a bigger temperature change in order for this guy to give up its heat, right? So it is actually the maximum heat transfer that you can get and still obey the first law of thermodynamics is the one associated with this maximum heat transfer in the fluid that has the smallest thermal capacity, right? So if you actually like think it through, it actually does make sense. But a lot of times, like I said, students get this mixed up. Q max, C min, right? They do actually go together in this construction, even though one is max, the other one's min. Okay, so having hopefully thought through that and following what I've said, we can now construct a series of equations around this thing called effectiveness, which I described before but did not define. So what is effectiveness? Effectiveness is basically the ratio of the real amount of heat exchange between the two fluid streams divided by the theoretical maximum between the two fluid streams, right? This thing that we calculated before. And in our case, where we've got CH greater than CC, right? Again, this works for other situations, but I want to just walk through, this one example for you. These guys, we already know the expression for Q max, right? It's C min times THI minus TCI, the inlet of the hot side minus the inlet of the cold side. So that's in the denominator. And then what is Q? That's the real heat transfer that occurs on the hot side of the heat exchanger. So that's the high temperature inlet minus the high temperature outlet multiplied by the thermal capacity of that high temperature fluid, right? The greater of the two, right? And so you might be looking at this and saying, well, gosh, this is going to be a number bigger than one, right? Because CH is bigger than C min. But remember, this temperature difference is the largest possible temperature difference, and this is the real temperature difference between the inlet and the outlet on the high side. And so this difference multiplied by this thermal capacity is actually smaller than this difference multiplied by this thermal capacity. That's kind of the genius of the effectiveness NTU method. It all happens up here. And you end up with an effectiveness that basically is bounded between 0 and 1, right? 0, if you have no heat transfer at all, right, which would be a really, really bad heat exchanger, but still possible. And then 1, if your heat exchanger is operating at its maximum possible heat transfer rate, which, of course, doesn't actually happen in the real world. You can't really have an effectiveness of 1, but it's a theoretical bound, right? So this effectiveness is bounded between 0 and 1. Um, just so that you know, and just so that you see it, the other possibility, right, which we're not going to talk about in this example, but just so you know that it's there, is the situation where Cmin is actually the hot stream, in which case the effectiveness just gets written this way, right? So it's Cmin times THI minus TCI, right? Same as before in the denominator. And then in the numerator, this is the heat transfer into the cold stream, right? So this is, again, the other situation, but just so that you can see, effectiveness gets written this way depending on which stream you selected as Cmin. The other one becomes what lives in the numerator. Okay, and then once you've got this, right now, we can write the expression for Q. This is what we're looking for, right? The heat exchange between the two fluid streams. So that's equal to the effectiveness times Cmin times the temperature difference between the hot stream and the cold stream at the inlets, right? So I'm just taking this equation and combining it with this equation and just solving for Q dot, right? So, okay. So if you follow me this far, okay. Hang on. So I ran these slides through AI just to see what it would say. And it like implored me to create this slide. So I'm like, okay, bro, make it for me. Like, this is like extra stuff. The students already know this, but it's like, no, you need this or the students aren't going to understand. So, okay, so here's the AI slide. The AI, see, I see here, AI reviewed my slides and demanded that I do this, right? And here's my AI trying to, like, force this on me and you. So the AI would like you to understand why effectiveness is limited. And effectiveness compares the actual heat transfer to the maximum possible heat transfer. I think you guys got that. So here's what's happening in a real heat exchanger, right? So you have the fluid on the high side, the hot side, entering and leaving, and you have the fluid on the cold side entering and leaving, and it's like, transferring thermal energy internally. Meanwhile, here's the length of the heat exchanger, here's those two temperatures, and the hot stream is getting colder and colder and colder, and the cold stream is getting hotter, 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 right? And they exit before those two temperatures are able to match each other, right? You could have an infinitely long heat exchanger, and these two would actually match, in which case you would have an effectiveness of 1, but that's an infinitely long heat exchanger, which is impossible. So the AI then came up with, and I love this, right? This is like all horrible and pixelated, right? This is why I do not use AI to generate slides, right? You guys are all like, why is Trom so slow? Trom is slow because he still does everything by hand. Because if you use AI, it comes out wrong, or at least you have to check it and iterate a bunch of times. Just faster and probably more accurate for me to do it. Anyway, so there's a typo here, right? Which you gotta be careful when you use AI. You gotta check it because AI makes mistakes. In this case, it was a ideal heel exchanger. Okay, yuck. So anyway, we've got our perfect ideal heel exchanger, ideal heat exchanger. Everything is the same: hot fluid entering on the top side, cold fluid entering on the bottom side. But this heat exchanger is either so long or so effective that these two temperatures touch each other by the time the fluid exits the heat exchanger. There's no temperature difference. And this is a situation where no additional heat can be transferred from the hot stream to the cold stream, right? Because they're at the same temperature. No temperature difference remains, no heat exchange, right? So this would be a heat exchanger that has an effectiveness of 1. So the AI would like you to know that the actual rate of heat transfer, which is UA delta T log mean, right? We figured this out in the log mean temperature lecture 7, is less than the maximum. So we can take the ratio of the actual heat transfer and the maximum and get this thing called effectiveness. And then We can calculate the maximum possible value by, again, taking the thermal capacity of whatever stream has the lower value of thermal capacity and then multiplying that by this maximum temperature difference, right? That'll give you the maximum possible amount of heat transfer. Okay, so the key idea, according to the Terminator here, is effectiveness tells us how close the real heat exchanger gets to the ideal maximum performance, right? So and again, it's bounded between 0 and 1. So a heat exchanger with an effectiveness approaching 1 is more like this situation, where you have like, an incredibly good heat exchanger. Um, yeah, okay, let's leave it there because, like, I think you guys know this already, but now the AI is happy. So okay, moving on. All right, so as we will discover in a second, here, let me fast forward so that you see these things, right? There's all these tables in the book. There's also figures in the book, right? These like figures. So we'll get to that. But what we need is a way to relate effectiveness to this thing called NTU. What is NTU? Well, NTU is number of transfer units. I have no idea where that term came from. It doesn't really make any sense. I accidentally wrote number of thermal units when I originally wrote the slides. Then I'm like, no, that's not right. It's transfer units. But it's effectively the ratio of UA, right? This is the uh, internal not resistance, but 1 over resistance, right? So the conductance, there we go. Internal conductance of the heat exchanger times the available area inside the heat exchanger, and then just divided by whatever the thermal capacity is of the stream that has the lower thermal capacity, right? So that's the definition of number of transfer units. It's basically just U times A for the heat exchanger, right? And then just kind of non-dimensionalized. I should mention that too. It's dimensionless, right? So we're just non-dimensionalizing by the thermal capacity of the stream that has the lower of the two thermal capacities. And so what we need is some functional relationship between NTU, the thermal capacities of my streams. So just a ratio of those, and that gets us to effectiveness, right? So what is that functional relationship? Okay, so it is different for every heat exchanger configuration, which is what makes this technique a little bit cumbersome. Right, LMTD is the same way though, right? It's you can do LMTD for a parallel flow or a counterflow heat exchanger, and all the math works out very easily. But as soon as you start dealing with like cross flows or shell and tubes, you have to use all kinds of, you guys should remember from the lecture, all kinds of like correction factors, and so you end up having to do all this anyway, right? With LMTD, LMTD is no better than Effectiveness-NTU in this way. It just kind of masks that extra complexity a little bit better because the correction factor for parallel or counterflow is just 1, right? So you don't have to worry about it for like those most standard conventional configurations. But for Effectiveness-NTU, you have to do this for every single possible configuration, including the simple ones. And so a lot of students sort of get this sense that Effectiveness-NTU is more cumbersome. It's really not. It's just the complexity is more upfront, right? It's not hidden the way it is in the LMTD method. Okay, so we're going to just consider a parallel flow heat exchanger, for which Cmin is equal to CH. I'm pretty sure. Is that what we did before? Oh, no. Okay. I might have to change this. I just did it backwards, right? So this all was based on this, but now I'm solving the other way around. So anyway, it works either way. It doesn't matter whether Cmin is CC or CH. The math comes out the same. It's just I'm following a derivation given in the book, and of course, this book is very scatterbrained. So apologies for that. I might fix it in the slides, but anyway, let's continue. So in this case, we have the thermal capacity of the high stream is the hot stream is the one that has the lower thermal capacity overall. Okay, so if we look back at the expression for effectiveness, so let's go back one slide, two slides, right? So here's the expression for effectiveness, right? But it's CH over C min times this temperature difference. And so here's that just same temperature difference where CH and C min are the same. Okay. And then here I am just actually doing the math, right? So I'm just taking a ratio of C min and C max, and that's just equal to these like mass flow rates times specific heats, and that gives me this temperature ratio here. And notice these are not the same, right? So we're going to have to do a little bit of manipulation to get this in the same form as this, so that we can get effectiveness and this ratio of thermal capacities related to each other, and that relationship is effectively NTU, right? So that's basically what we're doing here. Okay, so we have to cheat a little bit, right? Which is this. This is back to my like Pepsi versus Coke cartoon, right? So weirdly, effectiveness NTU is actually predicated on the LMTD derivation, although that is usually hidden, not revealed to students. But here it is, right? So here's like the secret underbelly for effectiveness NTU is, again, we're trying to relate this temperature ratio to this temperature ratio so that we can get an equation that has effectiveness and the thermal capacitance ratio together. And the way that we do that is to go back into LMTD and remember this expression, which is that the natural log of the temperature difference for stream 2 divided by the temperature difference for stream 1 is equal to minus UA, right? The heat transfer heat exchanger parameter multiplied by 1 over CH plus 1 over CC, the thermal capacity of the hot stream, thermal capacity of the cold stream. Okay, whew. So delta T2 and delta T1, well, what is that? That's just the hot side outlet minus the cold side outlet in the numerator, and then the hot side inlet and the cold side inlet in the denominator, right? That's what these represent, right? Because they are, if we go back, right, that's this, so over here, this change in temperature and this change in temperature. Thank you, AI. Right? Okay. And then if I do a little bit of manipulation here, it works out that this thing turns into this, right? So 1 plus C min over C max times negative UA over C min. And then I do a little bit more manipulation and I get this relationship here, right? Remember, this is an NTU, right? So NTU is sitting right here, right? So you can see that becomes NTU, which is here. This becomes this guy. This negative sign is that negative sign. And all I'm really doing in this step is I'm just saying, okay, I'm going to just exponentiate both sides, right? So I'm going to take this to the E. I'm going to take this to the E. And so I end up with this guy. Okay, so this is pretty good, right? Because now I have this kind of weird ratio of temperatures that at least has the same denominator as this guy, right? And it has NTU in it, and it has the ratio of heat capacities in it, right? So we're getting there. We remember previously I showed you guys like this ratio, which has yet another version of the ratio of temperatures in it, right? But this is my ratio of thermal capacities, right? So that lives there. And then from here, it's just like, oh my God, it's like pages and pages and pages of trying to get this ratio of temperatures to look like this ratio of temperatures to look like this ratio of temperatures to set them all equal to each other. And no, it's too much. So I just say here, substantial manipulations. If you want to see how it's done, look in the textbook. But the end result is that TH at the outlet minus TC at the outlet divided by TH at the inlet minus TC at the inlet is equal to 1 minus effectiveness times the ratio or times 1 plus the ratio of C min to C max, right? So if you want to see how this is done, it's in the book. It would have taken me like 10 slides, and probably not worth it, because it's just a matter of like pushing variables around in an equation until you can get this to look like this to look like this. And it does work. It's just very painful. So okay. So this is the same thing that I had written on the previous slide, just so that we can kind of see where everything comes from, right? And so now we have this relationship here from the LMTD manipulation. And then if you look back one slide, we have this relationship here. Oh, no, that's the relationship from the LMTD uh, expression. And then we have this relationship, which is from our definition of effectiveness and the ratio of C min C max. And the thing that I want you to see is check this out, right? This TH minus TC over TH minus TC outlet over inlet is the same as this one, right? So, wow, right? This whole thing, gobbledygook thing, right? This thing turns out to be equal to this thing, right? Through their temperature relationship. And that is the magic that gives us the expression, right? Because what we're originally going for was this, right? Some function that relates the effectiveness to the number of transfer units and the ratio of heat capacities. And boom, there it is, right? Okay. C min over C max, I'm going to invoke my usual, Mattrom law of conservation of chalk. And we're just going to write that as CR. So this is just now the ratio of heat capacities for the minimum and the maximum, whatever those happen to be for hot, cold, hot, doesn't matter, works either way. Um, and now that I have this relationship between NTU and effectiveness, which is only a function of this heat capacity ratio, now I can write this just as a simple expression that I can solve um, for effectiveness, knowing NTU and that heat capacity ratio, right? So this is like the final version of this equation, right? Which you could see all the pieces of it here, right? So here's like minus NTU times 1 minus CR sitting inside an exponential, right, which is right here, right? And then here's the 1. This 1 becomes this 1. And then here's 1 minus the ratio, right? Here's 1. 1 plus the ratio, 1 plus the ratio. And then effectiveness is all by itself, right? So you can actually see how this becomes that, right? Okay. And so these things all get, as I mentioned before, they get tabulated for all kinds of different heat exchanger types. So we have parallel flow, counterflow, shell and tube, one pass, multiple passes, cross flow, both fluids mixed, one fluid mixed, the other unmixed, both of them mixed. And then we have this kind of general expression for all heat exchangers where CR is equal to 0. This is probably the simplest of all the expressions, maybe with the exception of this one. But that one is for CR equals 1, where the two fluids are they have identical, right? So identical heat capacity. So okay, so let's go back here. So you can sort of see now, I think, where these come from, right? And so basically, what you have to do every time that you write one of these is the exact same series of steps where you write the effectiveness, and then you figure out the appropriate LMTD expression, and then you manipulate the ratio of the temperatures to get them to be equal to each other, and then out pops the expression, right? So that's where all of these come from. The good news is you don't have to do any of that because 200 years of engineers have done it for you, and it's all tabulated in the textbook. So it makes life much easier. But that's the underlying technique. Now there is a little bit of weirdness in a situation for which CR equals 0, right? And what does that mean? CR equals 0. That means that um, this is either 0 or this is infinity. So that actually happens in a boiler, in a condenser, or in a single stream heat exchanger where the other stream is basically not changing temperature, right? So this does actually happen. Um, so I say here for CR equals 0, effectiveness is given for all arrangements, right? So this is like a universal expression for all heat exchangers for which this situation is true. But how in the heck do you get CR equals 0? Well, the way that it comes about is if you look back into what's actually happening relative to the heat transfer between the two streams, the hot stream and the cold stream. What is the heat transfer? It's just the heat capacity times the temperature difference. And so if I rearrange this so that I'm solving for the heat capacity, it's just Q dot over delta T. But the change in temperature along one of these isothermal streams, right? So a boiler is not changing temperature because the fluid is changing from liquid to vapor. In a condenser, not changing temperature because it's changing from vapor to liquid. In a single stream heat exchanger, you basically got just one stream of fluid that's increasing or decreasing in temperature, and then just an incredibly massive thermal mass that's not changing in temperature as your source of heat or cold, right? And so that temperature difference for those specific situations where you have phase change or an incredibly massive thermal mass is zero, right? And so you end up with Q over zero, and that gives you a heat capacity of infinity, right? And that's going to be your maximum heat capacity, right? Because it can't get bigger than infinity. And so C max or C min over C max, which is the CR ratio, works out to be C min over infinity, which is zero, right? So you can actually kind of logically step your way through real situations where CR is zero. Again, boilers, condensers, evaporators, single stream heat exchangers. And so you get this really simple expression, and this expression is true regardless of what type of heat exchanger, what configuration of heat exchanger you're talking about, provided one of the two streams is constant temperature. So wanted to point that out as a special case because it is in the table kind of buried down here at the bottom, but it's a situation that comes up actually pretty often. In fact, when you guys talk with the GE Vernova guys tomorrow, I think they're having you design a power plant condenser. A power plant condenser is one of these situations, right? So you might actually take advantage of this expression to get some information about either the area or the effectiveness of that design problem. Anyway, just a preview. Okay, so I think we've now got this pretty well figured out, right? You guys have seen where at least one example of these equations come from. If you needed to, you could come up with all these expressions yourself, probably with the help of AI. Happily, you don't have to do that because they're all tabulated here. And there's like hundreds and hundreds and hundreds more. These are just kind of the standard ones that appear in the textbook. And you've got this special case for when you've got phase change in a constant temperature fluid. Okay, so I also want to point out that this whole thing can be reversed, right? So what we did before was we were looking for effectiveness as a function of NTU and ratio of heat capacities. You could also flip this around and find NTU as a function of effectiveness and ratio of heat capacities. And the reason that works is because all of these expressions are all just continuous functions that are plotted in two dimensions, right? So one axis is effectiveness, the other one is NTU. And so they just get represented this way, right? If you wanted to actually visually, graphically represent them. And so you can imagine, right, if I know NTU and the heat capacity ratio, I start here, I go up to where the heat capacity ratio crosses the NTU number, and then I go over and read off the effectiveness. But I can also just as well start out with an effectiveness, right? Read over to the appropriate capacitance ratio and then read down to find NTU, right? So this whole thing can also be done in reverse. And so, just to point out that these are in fact just continuous curves. And if you know effectiveness and CR, you can find NTU. If you know NTU and CR, you can find effectiveness, right? So what we happen to have here is the effectiveness for a parallel flow heat exchanger. This is for a counterflow heat exchanger. In case you just want sort of a quick and dirty, I don't need to do a calculation, I just want to kind of eyeball it, you're definitely welcome to use these figures instead of the actual equation. Just, be aware, as with all figures, you're kind of eyeballing things. And so you're getting kind of a, maybe plus or minus 10, 15% of the right answer. But in a lot of cases, especially for just back of the envelope type calculations, that is good enough. Okay, so in this world of solving for NTU rather than effectiveness, there's another table, right? So this is table 11.4, not to be confused with the table 11.3 in the book. Notice 11.3, what you're looking for is effectiveness and NTU. In table 11.4, you're looking for NTU and effectiveness, right? So it's basically just taking all those same equations that we found before and just flipping them around to solve for NTU instead of effectiveness, right? So no big deal mathematically. Okay, and There's a bunch, right? Right, like we've got shell and tube, we've got cross flow heat exchangers. So here are the expression, the figures for the shell and tube heat exchangers. Here they are for the cross flow heat exchangers, right? And as I was saying earlier, right, like the LMTD method does not actually work, at least not directly, for shell and tube and for crossflow. You need a correction factor. But for Effectiveness-NTU, that correction factor is just built into the derivation, right? So no need for a correction factor here because it's built into these expressions. So again, right, this sometimes from the like an outside view looks more complex than LMTD, but they're equally complex. It's just the complexity for LMTD is hidden in like a correction factor, whereas it's out in the open for Effectiveness-NTU. Okay, so a couple kind of things when we have these charts just to kind of look at, because we can look at what these trends are doing visually and get some interesting kind of information about that. So first one is if the NTU is less than about 0.25, you'll notice that all heat exchangers have approximately the same effectiveness, right? So like way down here, right at the bottom, right, the effectiveness is right about 0.1, right? So I say effectiveness 0.1, regardless of the ratio of heat capacities, right? So all of these curves all collapse into a single curve that has a value of about 0.1 for NTU of about a quarter, right? That the same is true here, right? The same is even true if I go back, right? So here's my um, a parallel and counterflow heat exchangers, same deal, right? If I get down here, right, effectiveness is about 0.1. Here it's about 0.1, right? So this is a really good, right? If you wanted a really, really, really back of the envelope calculation and you have a pretty crummy heat exchanger, right, effectiveness of 0.1 is not particularly good. You could just eyeball like the effectiveness and the NTU value if you're down at the far left-hand side of all these curves, right? Same thing is true for cross-flow heat exchangers, right? You're down here about a quarter NTU, and the effectiveness is about 0.1. Same is true here. Whoop, too far. Okay, so okay. So the other thing is for CR greater than 0. And NTU greater than 0.25, right? So we're like out here now. The counterflow heat exchanger is the most effective. So let's go back. Let's go back. Right. So what that means is if I'm looking, let's just put this to the test. So here's my parallel flow heat exchanger. Here's my counterflow heat exchanger. Let's just say they both have an NTU of 3 and they have a CR of 1, right? So the argument is that counterflow should be more effective than parallel flow. Let's see. So if I go 3 and I go up to 1 and I read across, I'm at an effectiveness of 0.5 for parallel flow. And if I'm at 3 and I read up to 1, yeah, right. And then I read over, right, I'm at about 0.75 for counterflow, right? So yes, that you can see it visually. This curve is like higher up on the effectiveness scale than this curve is. And that is just kind of a visual representation or a visual version of this statement that for CR greater than 0 and NTU greater than about a quarter, counterflow heat exchangers are most effective. And we saw that in LMTD, right? But now you have a way of actually visually seeing it in the world of Effectiveness-NTU. And then the last point here is for any exchanger, maximum minimum values of effectiveness are associated with CR equals 0 and CR equals 1, respectively. Yeah, so you get the maximum value of effectiveness for CR equals 0 and the minimum value of effectiveness for CR equals 1. Okay. Which right, you could also see that here, right? So if I've got a particular NTU, right, it doesn't matter whether it's shell and tube or what, but right, so this is CR equals 1, this is CR equals 0.75, 0.5, 0.25, 1, sorry, 0, and you can see that for any NTU value, the effectiveness basically goes up, right, as CR is going down, right? Same is true here. Same is true here, same is true here, right? So just, another kind of, you could see visually what's written here in words. Okay, so Here we have cross-flow heat exchangers, same story. Everything that I just said is true. This is just another chart that's representative of this set of equations. There is kind of a weird nuance here. Notice that there are mixed and unmixed, mixed and unmixed. What does that mean? Well, we've got here, we've got mixed and unmixed. So the terms mixed and unmixed are idealizations representing limiting cases of actual flow. So remember, when we were talking about LMTD, mixed meant that you had basically like a series of tubes with the cross flow not being constrained by like walls or fins or anything like that, right? Which allowed the fluid to mix as much as it wanted to in the cross flow direction over the tubes. Unmixed meant that there was some sort of fins or walls or something in the way that prevented that cross flow from mixing. Again, these are kind of limiting cases, right? The fluid is definitely going to mix even if it's right turbulent flow, even if it's between two plates, it's just going to mix less than if those plates weren't there. And so again, these represent kind of extreme idealizations. It doesn't show up in the book other than just a quick mention. There's no figure for it, but most heat exchanger flows are neither completely mixed or unmixed. And so there are effectiveness-NTU expressions that exist for all the different degrees of partial mixing, right? And you can see it's not like a dramatic difference between mixed and unmixed, right? But it's not trivial, or it's not totally, these curves don't fall right on top of each other. So if you're looking for like, doing detailed design work using Effectiveness-NTU and you have a heat exchanger where you're not quite mixed, you're not quite unmixed, your curve is right in here somewhere. And if being between these two extremes is not good enough, you know exactly where you are, you can go out into the literature and find the appropriate equation, the appropriate curve for a partially mixed situation. We don't have that in the textbook, but just so that you're aware that it's there and don't feel completely constrained by these two extremes. Okay. Um, so remember, all the way back in the beginning, I mentioned there's this thing called compact heat exchangers, and that's this section. So a compact heat exchanger, something like this, is used when you need extremely large heat transfer surface area per unit volume, right? So these things have got like tons of internal surface area to facilitate maximum heat transfer between hot streams and cold streams, and they are very, very small in size, right? Very, very compact. And so the metric that's usually used to describe these things is this value called A, which has really weird units, right? It's meter squared over meter cubed. And you might say to yourself, what? Like, why is that? It's not just 1/meter. Well, okay. Meter squared is the internal heat transfer exchange area, and meter cubed is the overall volume of the heat exchanger, right? So it does actually make sense to leave it as meter squared per meter cubed, right? Even though those units feel like they should cancel. Typically, these also appear when one of the fluids is a gas, because as we've talked about, gases have much lower forced convection coefficients than liquids do. We'll get into convection next week. And so you'll actually be able to calculate that and see that. But if you have gas, it has a really low convection coefficient. If you need to get high rates of heat transfer, you definitely need a lot of surface area to get away from that low H value. And so these guys are useful in those situations too, when you have mixed liquid gas. Okay. Heat transfer and flow characteristics have been determined for specific configurations. So for every one of these, you actually have to go to the manufacturer and find, because they're all different, right? And find the appropriate curve and then use that curve to back out the heat transfer behavior, the heat transfer performance of each one of these heat exchangers. The way that this normally works is the results are correlated in terms of the so-called Colburn J factor. Colburn was a heat transfer experimentalist who came up with this thing called J factor. So here it is, JH is equal to, oh man, the Stanton number, which is a dimensionless number that you might have seen in fluids, times the Prandtl number, which is another dimensionless number, which you've definitely seen in fluids, raised to the 2/3 power. The Reynolds number, which you've seen in fluids, except this has got a slightly different form to it. G times the hydraulic diameter divided by the fluid viscosity. Um, and then just so, because you probably have not seen it before, the Stanton number is just a ratio of um, H over GCP. What in the heck is H? Or sorry, eight. Well, let's do H. Just since I said that, H is a convection coefficient, right? So that's a value you need to know to find U. And then what in the heck is G? Well, G is kind of like a mass flow rate. Um, right? So it's a density times V max. So it's essentially like a velocity kind of, if you will, right? And that sort of makes sense because this is where velocity would live in the Reynolds number, and this is where velocity would live in the Stanton number. So um, how do you figure out that velocity? Well, okay, it's the density times V max, which is all of these different ratios, right? So you could take the mass flow rate and you can divide by the cross-sectional area perpendicular to the flow direction, or you can divide by the ratio of minimum fin free passage flow uh, and frontal area of the heat exchanger. But these are all different ways to get to G just based on like the mass flow rate and the geometry of the heat exchanger, right? So these values, A sub FF or A sub FR and sigma, should be given by the manufacturer, and you as the engineer know how much mass flow you're putting through this thing. And so you take the mass flow, you divide by the area, and you get a velocity essentially, which then goes into Stanton number, Reynolds number, and then these feed into the Colburn J factor. Okay, so let's that's a lot, right? So let's just take a look at how this actually works, right? So and I'm going to kind of flip back and forth between a couple of slides here, right? Um, so just a few more little tidbits. So AF over A for calculation purposes is the ratio of fin total area heat transfer surface. Sorry, fin. Let's try again. AF over A is the ratio of fin area to total heat transfer surface area. That's what I wanted to say. And other geometric parameters must be listed for each configuration, right? So you can see here, this is actually one of these Colburn J factor charts, and you can see they're giving like the separation distance and the diameters of the tubes and the fins, right? So AF over A is used to evaluate the temperature effectiveness, which we've seen when we did fins, A to naught. Alpha determines the required heat exchanger volume after the total heat area is found, right? So remember back here, this is alpha. So you calculate using this Colburn J factor, the M squared value. You know the A value because that's given by the manufacturer, and that gives you the M cube value. So how much volume this thing takes up, which that's typically a important consideration for compact heat exchangers. The reason that they're compact is they have to fit into a small volume, right? So you want to know what that volume is. And then for performance calculation, if you do this in the other direction, right, you know how much volume you have and you're trying to figure out the surface area needed to give the appropriate amount of heat transfer, then you can use that A value to figure out how much area is needed from a given volume, right? So this is if you know the area and you're looking for the volume. This is if you know the volume and you're looking for the area. Okay, so how does this work? So here's the steps for the calculation process for compact heat exchangers. So we are going to determine the average convection coefficient H of the fin surfaces. We need H to get to U, right? Remember we talked about how to generate U from a set of resistances, right? Resistances in series in the LMTD method. So we want H to get to U. How do we get to H? Okay, so we're going to start out with knowing the mass flow rate of the fluids that we're putting through the heat exchanger. We're going to use the given geometry, either the cross-sectional area perpendicular to the flow, right? So that, or the frontal area of the exchanger, like that. And we're going to calculate the appropriate G. From G, we get to the Reynolds number, right? Because G goes into the Reynolds number. We know the viscosity of the fluid. We're going to take the geometry of one of the channels that the fluid is running through and calculate its hydraulic diameter. So this G velocity times hydraulic diameter divided by viscosity gives us the Reynolds number. From the Reynolds number, we can find the Colburn J factor. How do you do that? That's what's on this chart, right? So here's all the Reynolds numbers on the x-axis for this type of heat exchanger. Here's all the Reynolds numbers on the x-axis for this other kind of heat exchanger. Here are the J factors, and here's the curve that relates the Reynolds number to the J factor, right? So you get the Reynolds number, and then you go to the chart and you find, let's say, Reynolds number 4. I'm just making this up. Reynolds number 4, right? And then you go up to here on the J factor curve, and then you read over, and it's 0.009 is your J factor, right? So over here, if we had a Reynolds number of 4, we read up here to when it hits the J factor line, and then we read across at 0.006, right? These are two different heat exchangers. These are curves from the manufacturer. That's typically where that value comes from. Okay. Okay, great. So we got to J, right? So now we've got J. We need to get to H because we need H to find U. How do we get to H? Well, J is just the Stanton number times the Prandtl number to 2/3. Prandtl number is, you just look it up, right? Prandtl number is a constant that's based on, it's a material constant, right? So air has a certain Prandtl number, water has a certain Prandtl number, function of temperature, right? So you need to make a guess about what the average temperature is, but you could basically look up the Prandtl number for whatever working fluid you've got. So this number is a lookup number, and then you got this guy, and now you solve for the Stanton number, right? Then finally, last step, we take the Stanton number, we rearrange the Stanton number expression, and we solve for H, right? So take Stanton number times G, which you know, times CP. This is the specific heat of the fluid. You get H, and out pops H. Whoa, okay, now you got H, right? And so now from H, you can determine the overall heat transfer coefficient, right? So remember, again, normally, right, there's like a stack up of resistances, right? There's resistances associated with the forced convection coefficient H, which we just found. There's resistances associated with the conduction through the tube walls. The whole point of these compact heat exchangers is we're trying to like maximize the heat transfer while minimizing the volume, right? So typically you just take the H value for the hot side, the H value for the cold side, add them together. That's typically your U value, right? There's very little other other resistances to heat transfer because everything else internally is metal and very thin. So small resistances to heat transfer through conduction. Okay, and then once you know U and A, the internal area for heat transfer, which is given by the manufacturer, now we know NTU, right? Because let's go back all the way to, right? So you know U, you know A, and you know the fluid that you're running through your whatever hot side or cold side of your heat exchanger, and so you can calculate NTU. Now that you have NTU, you can use the effectiveness-NTU method to find effectiveness, and then you can use effectiveness, as we've just talked about, to get the total heat transfer, right? So it's a kind of long, painful, convoluted process, but I hope you can kind of follow my logic and see how you could actually carry out this calculation if given values like alpha, total internal surface area for heat exchange, and this J chart. Okay. Whew. Now, why doesn't everybody just buy a compact heat exchanger and call it a day, right? Why do we have these huge, clunking, massive, enormous heat exchangers when everything could just be compact and everyone would be happy, right? Small heat exchangers would make the world a happy place, except there's a trade-off, right? Which is if you've got this tiny little heat exchanger, you guys know what's coming. You're going to get an enormous pressure loss across this heat exchanger. Sometimes that pressure loss can be so high that it requires pumping power high enough, right? Remember, again, everything in here is very thin, right? It's all very thin copper, very thin aluminum, right? We're trying to maximize heat transfer, so we want all of these thin little channels. And a lot of times the two fluids running through at different pressures, right? You've got a liquid that you're trying to shove through, and you've got gas that you're trying to shove through, so the pressures are going to be different. It's not impossible to actually exceed the mechanical failure pressure of the components inside the heat exchanger, right? Because you need so much pressure to push the fluid through. So you got to make sure that you're not exceeding that pressure capacity of the heat exchanger because you're trying to push fluid through so fast that you exceed the operating pressure of the thing, right? So you need to know the pressure loss so that you know how much pumping power is required so that you don't exceed the pressure specifications of your compact heat exchanger and blow it up, right? So, and maybe also as a secondary but still important consideration, the required pumping power, right? You might want to know how much power you're putting into the pump to get the fluid to go through at the M dot that's required to get this H value for you to do your calculation to begin with. Okay, so often critical is pressure loss and then associated pumping power across the compact heat exchanger. And so the book gives this expression. They explain what all these terms are and where they come from. One of them is associated with viscosity. The other one is associated with losses. This guy you recognize, right? That's the friction factor from the Darcy-Weisbach equation. If you took fluids with me, you know that that's like my favorite fluids equation. And where does this friction factor come from? Well, right there, right? So you know the Reynolds number because you calculated it before. And now you just read the Reynolds number up to the line and then you read over, and now you've got the friction factor. Same thing here, right? You just read up and then over, and you got the friction factor to plug into this part of the equation. Everything else is already calculated or given by the manufacturer, right? We had to calculate G way up here, right? That's the velocity. VI is the fluid inlet specific volume, right? So, temperature, pressure, you can find specific volume. It's 1 over density. This should read V out, not V in. So I messed that up. I'll have to change that. Let me make a note to myself for slide 15. You guys will see it corrected when you look at the final slides. So VI, I should say mu I is fluid inlet specific volume. Mu out is fluid outlet specific volume. And then this should read mu M, right? It's this one here, M for mean, not 0, but M. And that's the mean specific volume of the two fluids, which goes there to the equation, right? So all these things, right? Here's I again, here's mu naught, here's mu I. Sigma, just to remind everybody, is the ratio of minimum fin passages free flow area. So this is a ratio of minimum fin passages free flow. Okay. So this is a value that would be given by the manufacturer, right? It's basically a ratio of areas. Okay. Okay, so I say here, this delta P, oh God, okay. Yeah. This is a little note, right? So you can calculate delta P. We'll get to this in a second. This delta P, by the way, is the pressure here at the inlet to here at the outlet, or here at the inlet to here at the outlet for your two fluid streams. The book would like to remind you that the delta P expression does not account for ductwork losses in transporting fluids to or from the heat exchanger, right? So if you have your balance of plant, right, all of your piping and tubing and everything coming out, that delta P that we just calculated in this equation does not account for all that extra plumbing, right, that's required to get the fluid here to begin with. That delta P is just for the compact heat exchanger itself. But the good news is you guys have all taken fluids. Fluids is a prerequisite to heat transfer. You don't have a choice. And so you're able to estimate the inlet and outlet losses from all of that piping using the appropriate contraction and expansion charts from your fluids book. At least if you took fluids from me, you know how to do that. Maybe somebody else didn't teach you that, but they should have. So, okay, that's compact heat exchangers. Whew. In summary, heat exchanger design and performance calculations. There are two general heat exchanger problems that engineers in practice commonly encounter. The first is the heat exchanger design problem. So this is a situation where everything is known about the fluid inlet temperatures, the flow rates, and the desired outlet temperatures, right? So you basically know everything that's going into and out of the heat exchanger. And your job is to either design or specify a specific heat exchanger that's able to achieve these outlet conditions given these inlet conditions. right? So it's up to you to determine the heat exchanger size, which really, for these purposes, is the heat transfer surface area, right? So that A value inside the heat exchanger to achieve your target outlet temperatures. And in this case, you would apply the effectiveness-NTU method by calculating the effectiveness. So this is like needed effectiveness, right? Because you're looking for how much heat transfer is required to get these outlet conditions, and CR, which is from your fluid choice, right? So your working fluids are going to have um, mass flow rates that are known, and they're going to have specific heats, which are known because you select what working fluids you're dealing with. Um, so you can basically calculate these two, and then you're going to use the appropriate from your choices, your design choices, and then you're going to use the appropriate equation or chart um, for NTU ultimately to determine A, right? Because right? NTU has got A in it, it's got U in it. You presumably know the U from the heat flux, and so now you can find the A. Okay. And then there's the other type of problem, right? So heat exchanger performance calculations. This is a situation where you've got an off-the-shelf heat exchanger that comes from a vendor, right? And you're trying to evaluate whether a heat exchanger from a vendor is going to meet your requirements. So you're analyzing an existing heat exchanger to determine its heat transfer and fluid outlet temperatures for a prescribed set of inlet conditions, so inlet temperatures and mass flow rates of hot fluid and cold fluid. So you can also use the effectiveness-NTU method in this case by starting with Q dot and calculating the required NTU, Cmin, and Cmax, right? So you determine those, and then you use an appropriate equation or chart, effectiveness-NTU equation or chart, to find the needed effectiveness for each given heat exchanger type, and then that tells you whether or not you have a heat exchanger selected off the shelf that'll give you enough heat transfer to meet your requirements. Along the way, you can also find the unknowns if you need them, right? So you can find the Q dot from this step, and once you have the Q dot, you can find high temperature inlet, high temperature outlet, cold temperature inlet, cold temperature outlet, whatever's not given as needed. And then you can compute Q dot, and from Q dot and the effectiveness, you can compute Q dot max, right? Q dot max. And then from Q dot max and the effectiveness, you can find Q dot, which is what you're actually going for, right? To find whether something that you select off the shelf will actually have enough heat transfer capacity to reject the heat that you're trying to get rid of by selecting a particular type of heat exchanger. Whew. Okay, let's do a couple of examples. I got two of them for you. Okay, so example one, we're going to consider a very long, and that should be a hint, very long concentric tube heat exchanger having hot and cold water, inlet temperatures of 358 Kelvin and 288 Kelvin, respectively. Mass flow rate of the hot water is twice that of the cold water, right? So that tells us something about M dot and about C. Assuming equivalent hot and cold specific heats. Equivalent hot and cold specific heats. Determine the hot water outlet temperatures for counterflow and parallel flow. Okay, so let's tackle this one. So I have here, as always, right, whenever you start any sort of engineering problem, particularly energy thermal fluids, you always want a sketch of some kind. I just stole my own figures from the LMTD lecture, so you've seen these before, and I'm just superimposing for parallel flow and counterflow a control volume around the outside of both of those heat exchangers so that we can just analyze them using the first law of thermodynamics. I'm also going to make a set of I'm going to make some assumptions. These are just the standard heat exchanger analysis assumptions that we already talked about in the LMTD lecture. But just as a reminder, we're going to imagine this thing is perfectly insulated on the outside. So the only heat exchange is between the hot fluid and the cold fluid internal to the heat exchanger. We're going to imagine that the axial tube conduction is negligible, right? So even if it's hot on this side and cold on this side, none of the heat is transferring in the axial direction down the tube through conduction. It's all just transferring across through conduction and convection from the hot fluid to the cold fluid. We're going to ignore any changes in potential or kinetic energy because we're going to assume they're negligible. We're going to assume that all fluid properties and specific heats are constant, and that the overall heat transfer coefficient U is also constant, right? So given those assumptions, I should be able to apply the first law of thermodynamics and pop out a equation that represents just the energy flux between the hot flow and the cold flow inside this heat exchanger. Now, I don't know that I've ever used the term trivial new thing in this class. We talked a lot about it in fluids, right? Because really, like these problems are often so, oh, what's the right word? I don't want to say easy because they're not easy, but um, like once you know how to solve one of these problems, it's really hard to make the problem very challenging unless you add some trivial new thing that has like nothing to do with energy thermal fluids and make that kind of a barrier for people to have to solve before they can actually solve the underlying problem, right? We see this in fluids all the time. Fluids problems are all the same. And then to make them kind of interesting and complicated, you add like, hop on one foot and turn around counterclockwise on Thursday, right? To like get to the volume flow rate that you then need to actually solve the problem, right? So I always try, it's a term we use at MIT. I always try to point out like what the trivial new thing is so that students can kind of see like this is actually just a standard fluids problem, and then there's some weird kind of trivial thing built onto it to make it harder. But it's really just an easy fluids problem with this hard thing kind of tacked on, sometimes like a cancer. And so what's the trivial new thing here? The trivial new thing is very long concentric tube heat exchanger, right? Why is that the trivial new thing? Well, if we go all the way back to the Terminator, too far. There he is, right? What happens if you have an infinitely long heat exchanger? The temperatures at the outlets for the hot stream and the cold stream are one and the same, right? And so that's not what normally happens in a heat exchanger, right? Normally those temperatures are different, but here, because it's an infinitely long heat exchanger, or I say very long heat exchanger, or ideal heat exchanger if you trust the AI, those temperatures are the same. You could not solve this problem unless you had that realization, right? And you can imagine going around and around and around in circles, applying the first law, trying to figure out all kinds of stuff to try to find the conditions at the outlet for this thing and not being able to find them unless you noticed very long heat exchanger and realized that very long meant infinitely long. And so what that means, right, very long, is that you can assume that for parallel flow, the outlet temperatures are the same. So T hot outlet and T cold outlet are the same because the outlets are going in the same direction. And so the flows are going in the same direction. So the outlets are going to be the same temperature, right? That was, right? That's this example, right? Same temperature. Or for a counterflow heat exchanger, whoops, too far. For a counterflow heat exchanger, the inlet and I should say the hot inlet and the cold outlet are the same because in this case, the fluids are moving in the opposite direction, but an infinitely long heat exchanger. And so the cold stream has enough time to get up to the temperature of the hot stream at the outlet, which corresponds to the inlet for counterflow, right? Okay, so that's the trivial new thing, right? If you hadn't realized that, you would be screwed. But once you realize that, this problem is, not too difficult, right? But it's this realization that makes this hard. Okay, now that we've got that realization, I say here, since fluid has time to reach asymptotic temperature. Yeah, that's what I mean by this. Okay, so we're now going to apply the first law of thermodynamics. We're going to do it for both of these at the same time because the answer comes out the same. So I assumed the heat exchanger is insulated, so I have no heat transfer from the environment into either one of my heat exchangers. So Q in, Q out are zero. I have no shaft work, nothing crossing the system boundary that's turning, no electricity coming in, right? So shaft work is zero, shaft work out is zero. I'm in steady state. I hope I said that somewhere. Uh-oh. Huh, okay, I didn't. Well, okay, that's an assumption as well. I should add that we're in steady state. Standard heat. Yeah, huh, okay, steady state. So we'll add that in the slides. Let me actually make a note to myself. This is slide 17. Okay, got to be in steady state, otherwise this doesn't work. So this term goes away. and then potential and kinetic energy changes are negligible. So that allows me to get the kinetic energy term and the potential energy term square out of the inlet and the outlet. Those all go away. And voila, this is what we have as a result of the first law of thermodynamics. So the sum of mass flux out times the enthalpies out minus the sum of mass fluxes in times the enthalpies in equals 0. And if I break this down, remembering that fluid properties in specific heats are constant, right? H is equal to just CPT if CP is constant. And so I could take this guy and I can convert it into this. So I've got my m dot times CP for the cold stream times C for the cold outlet, m dot times CP for the hot stream times temperature for the hot stream outlet. That is this term, right? And then this term is this guy and this guy, this negative sign and this negative sign comes from that negative sign. And that's all equal to 0, which I need to add that equals 0, equals 0. Okay, let's add that equals 0. Okay. Right. And then this is just law of conservation of chalk. I'm just writing m dot c, CP C as just capital C. And then same thing here for the hot stream, capital CH. And then I'm told in the problem, right, it's subtle, but it's there. Mass flow rate of hot water is twice that of cold water. Well, if I assume that the CPs are all the same anyway, what that means is that just this, let's see, which was which? Mass flow rate of hot water. Okay. What this means is that 2 times C cold is equal to C hot, right? Because the mass flow rates, one is double the other one, and the CPs are the same. So that's where that comes from. Okay. And so now I'm just taking this equation and I'm rewriting it this way to put it into kind of my heat exchanger parlance, right? And then in the next step, I'm going to just move C, which one did I move? Oh, okay. I'm actually moving this guy to the other side of the equation, right? And in so doing, notice that I'm replacing CH with 2CC, right? So this CH becomes 2CC, and then I'm switching these two, right? Switching these two because I'm moving this to the other side of the equation. So that's like just multiplying by -1. And now CC and CC are the same value, so those cancel out, and I just get this guy. And so now this is the equation that I'm going to use to try to find. Remember, what I'm looking for is the hot water outlet temperature for counterflow and parallel flow. Okay, so I did parallel flow first. Now, remember, right, the trivial new thing was that the hot outlet temperature has to equal the cold outlet temperature for parallel flow. And for counterflow, the hot inlet temperature has to equal the outlet cold temperature. So if I didn't have that information, I would be stuck with this equation, one equation, two unknowns, and I would be screwed, right? I wouldn't be able to solve this. So again, trivial new thing. So this is what it looks like, right? The cold stream gets hotter and hotter and hotter. The hot stream gets colder and colder and colder. They meet here at some, infinite distance away. And that allows me to say, okay, I'm going to just take this guy and I'm going to plug in this guy, right, which is here. And now I have one equation, one unknown, right? And now I can solve for it and I get 334.82 Kelvin for parallel flow. For counterflow, similar thing happens, right? The fluid that's cold enters here and heats up until it reaches 85C, which is the inlet temperature for the hot stream, which enters and cools down, right? And so same story, right? I have this expression, and all I'm going to do is just substitute this guy in for this guy. And now I have one equation, one unknown. So I put in all the things that I know, the inlet conditions that are already given, and out pops T sub H at the outlet, which is 323.15 Kelvin, right? And I checked these against the answers in the book, and they're right. So that's how to do that one. Okay. Last example, and then we'll wrap up. You guys have already seen this example. You saw it in the LMTD lecture. I'm going to solve the exact same problem, but I'm going to solve it using Effectiveness-NTU just to show you that you basically get the same answer either way, right? Doesn't matter which approach you use. Sometimes LMTD is better. Sometimes Effectiveness-NTU is better. This problem is written in such a way that it actually Effectiveness-NTU is better. If you remember when we did it with LMTD, we had to look up correction factor, right? Which was an extra annoying step. But you get the same answer. Okay, so we're gonna again consider a single pass cross flow heat exchanger with a surface area of 10 square meters. Cold fluid has a heat capacity rate of 2,310 watts per Kelvin and an inlet and outlet temperatures of 303 Kelvin and 423 Kelvin, respectively. Hot fluid has a heat capacity rate of 2080 watts per Kelvin and an inlet temperature of 598 Kelvin. Um, Notice these are all in Kelvin, right? When I took this problem from the book, it was all in Celsius and I converted it to Kelvin for you. You're welcome. I say this in every lecture. I'm going to say it again. If you encounter degrees Fahrenheit, Rankine, Celsius, anything that's not Kelvin, please, please, please. I don't care if you're like, a America units person, like, please convert it to Kelvin, do all your math in Kelvin so there's no problem with division, multiplication, right? No issues with non-absolute temperatures. And then when you get to the end, convert it back to whatever units you want. But all your heat transfer calculation should always be done in Kelvin so you never run into problems. Thermo too, same story. Fluids, same story. Always use Kelvin, never use Celsius or Fahrenheit or Rankine for that matter, even though Rankine is absolute, because just you get into trouble by accidentally dividing temperatures that are not absolute temperatures and getting your math screwed up. So please use Kelvin. And I've already done it for you here, so you don't have to. Okay. If the cold fluid can be considered mixed and the hot fluid unmixed, so that gives us a hint about what to use. Find the overall heat transfer coefficient U and the outlet temperatures of the hot fluid. Okay, so I'm going to use my normal heat exchanger analysis assumptions, which we've gone through before. I'm going to add to this slide steady state. I borrowed this from the book, and there's like no mention of steady state, right? Yeah, it's not in there. It's crazy. So steady state plus these. Okay. I am immediately, because I already know that I'm solving this using Effectiveness-NTU. I'm immediately going to find the appropriate tables, right? So these are the equations in the tables for, I know, effectiveness and the heat capacity ratio, and I want to solve for NTU, or these are I know the heat capacity ratio and the NTU value, and I'm going to solve for effectiveness, right? I'm not sure yet which one of those I'm going to use, but I'm just going to gather up that information in case I need it. And then this is the appropriate figure in case I want to use a figure instead of the tables, right? I use the tables usually for accuracy, and the figures just kind of for eyeballing quick back of the envelope type calculations. Okay. Ooh. Huh, I don't know why that is that way. Weird. Okay, this this is a green check mark, but it came out all goofy. So we've already solved this, right? We solved it in the previous lecture. So we know that the LMTD value that we got is that U is equal to 181.0 watts per meter squared Kelvin. Should be a green check mark. I will fix that in the final version of the slides. So we already know where we're going. And what I want to show you here is that you get the same answer, right? If you do it this way, because these two methods are not necessarily interchangeable, but they're both correct. And you just pick the one that's most convenient for you, given what you know about the problem. Okay, so here's how we're gonna, wait a minute, what is this? Oh, okay, I was gonna say, oh my God, I didn't change this. No. Okay, so here's what we're going to do. As mentioned, it is possible to use LMTD with F correction. We did that before, or to use Effectiveness-NTU. We're going to use Effectiveness-NTU this time just to prove to you that it's the same solution. First, we're going to determine which flow stream is Cmin and which is Cmax. We're already basically told that, right? But we need to codify it. We're going to select the correct Effectiveness-NTU equation from the tables, or if you want, you can use a chart, but less precise. Then we're going to find Q dot, Q dot max, CR, and effectiveness. And we're going to use the appropriate Effectiveness-NTU relation to find NTU. And then we're going to use NTU to find the known, to find U, because we know A, right? A is given as 10 meters squared, right? So that's our kind of sequence. Okay, so let's just jump right into it. Okay, so yes, we're going to use Effectiveness-NTU. First thing is we're going to determine which stream is Cmin and which is Cmax. Okay, so we're told cold fluid, which has a C of 2310. That's mixed. We don't care about that yet. The hot fluid is 2080 watts per Kelvin. That one's unmixed. We don't care about that yet. So this number is less than this number, and that means that the hot fluid is the one that is Cmin. Yeah, yeah, right. Okay, so that's the one that's Cmin. Okay, and also, by the way, since we know that we are trying to find effectiveness in CR and then plugging into solve NTU, we're going to remember I just pulled all of this out of the book, right? We're actually going to use one of these, and that means we have to figure out which one of the fluids is mixed and which one is unmixed. So we're told the cold fluid, which is Cmax, is mixed, and the hot fluid, which is Cmin, is unmixed, right? So Cmax is mixed, Cmin is unmixed, and that arrangement corresponds to this first of the two options in the in the NTU expression. Cmax mixed, Cmin unmixed, right? Cmax mixed, Cmin unmixed, right? Okay, so this is the equation that we're going to use moving forward. So you guys will see this one appear once I get CR and effectiveness figured out, and I'm looking for NTU. Okay, so let's march on. So we are so we just did this one, determine which flow stream is Cmin and Cmax. Oh, and we also did this one. So select the correct NTU equation from the tables by basically deciding which one is mixed and which one is unmixed. Okay, cool. So now we are on our way to finding Q dot max, CR, and effectiveness. So here we are. CR, which is the ratio of Cmin to Cmax, is 2080 divided by 2310 watts per meter Kelvin. It's dimensionless. It's a ratio. It's 0.9 when you do the math. We also know that the Q is, let me think about this for a second. Oh, were we given these temperatures? Wow, that's very generous of them. Yeah, cold fluid heat capacity, this inlet outlet temperature 303 and 423 respectively. Wow. Okay. So that's really nice of them. They actually gave us those two temperatures, and we know the C value because that was given too. So we can actually just calculate Q dot straight away, right? So there it is, right? 277,200 watts. That's Q. We can also find Q max because we know that the hot fluid is Cmin. We know its C value, right? So there it is. And then we know THN and CIN. Let's make sure that we know CIN. Cold, yeah. Hot. Oh, yeah. Okay, here. Hot inlet temperature of 598, right? Okay. Yeah. So that's known, right? So we're going to plug in and we're going to find that 613,600 watts. And because we know Q and Q max, we can find effectiveness. Voila, there it is, 0.452. Amazing. Okay, so, wow, this was way easier than the LMTD approach. I'm waiting for like all hell to break loose, but it's actually not bad at all, right? Because I'm already to effectiveness. So I've got my effectiveness, I've got my CR, I've got my appropriate equation for NTU. So I'm just going to plug in, right? And here I am doing it. So I'm solving for NTU. Here's the equation. Here I am plugging in my values, 0.9 for CR, 0.452 for effectiveness, and out pops 0.867. That's my NTU. And now that I know NTU, I can use the equation that relates NTU and UA, which, oh, I didn't write it anywhere. Well, okay. Oh, it's sort of right here, right? It's normally you see this as NTU equals UA over Cmin, but that's fine. You guys, I've seen that already. So I'm just going to rearrange this. I'm going to solve for U, right? So here I am rearranging, and then here I am putting in my Cmin, my NTU that I solved before, my 10 meters squared, which is the given internal surface area, right? 10 meters squared, given internal surface area. And out pops 180.4 watts per meter squared Kelvin. Okay, and, right? When we did it with the LMTD method, we got 181, right? These are close enough for, engineering, they're the same number, right? It's probably just a rounding error there that causes it to be slightly different, but just, less than 1% difference. So voila, we get the same answer. Okay, so hopefully it was helpful to see going through that technique both ways to see how it was done. Again, when we did it with LMTD, we had to find all kinds of correction factors, and it was a god-awful mess. With Effectiveness-NTU, it's like super fast, right? I did it in one slide. So that just gives you a sense, right? Both of the approaches are correct. There's just sometimes one approach is more efficient than the other. Usually when you've got like shell and tube heat exchangers, or you've got crossflow heat exchangers, all of the complexity is already accounted for in the Effectiveness-NTU equation. So that's usually the way to go for those kinds of problems, unless you're given a problem that's specifically set up so it wants to be solved by LMTD. Okay, that brings us to the end. This is my last slide. So thanks for your time and attention, and I'll see you for the next one.